All right, so we just finished learning Newton's laws of motion, and in the last lesson tried motivating that there are situations with the force where we cannot really and straightforwardly use the Newton's equations of motion or Newton's laws, particularly the Newton's second law, to solve the problem. And the example was this, for example, that if you have an object, you throw it with very far away from the surface of Earth, all right, and the distance between the object and the center of the Earth is r. Okay, then the force of gravity acting on this object here would be F G m over r squared. Okay, so we don't really know what the force is without knowing how far away the object is or the position of the object, but that is the very thing that we don't know, and we try to find using the Newton's second law, right? F is equal to ma. So we need to first know the force. Once we know the force, we figure out the acceleration. Once we figure out the acceleration, we figure out the velocity. And from the velocity, we figure out the position as a function of time. So if we have a force that depends on position like this, we plug back in here, we are stuck because we don't know we don't know the force because we do not know the position vector. If we try to find the position vector from the from the Newton's second law, we cannot because we don't know the force. So that is the type of problems where we, although that if you want to use the more mathematical language, Newton's second law is not really an algebraic equation. It is a differential equation, a second order differential equation. Okay. So if I write it in one dimension, this is what Newton's second law is. Okay. And if you have a force which depends on position, then this equation becomes a non-linear differential equation. There are ways to solve it, but let's not get into that. Okay. And to work around this apparent problem and to make it easier to solve such kind of problem, we introduce a couple of new concepts. Okay, namely the work and energy. Okay, and hopefully by the end of this chapter, the work energy chapter, we would have learned the importance of the concepts of work and energy, and how and when they are helpful where Newton's second law becomes really unhelpful. But let me just say it very clearly and from the very beginning, whatever relationships that we are going to work out now, they are not outside of the realm of the Newton's laws. Okay, we get these relations from Newton's laws, and it does not mean that that we are introducing some new fundamental laws. We are not introducing anything new. So the mechanics, the Newtonian mechanics, or the mechanics that we are studying in this course remains rooted in the fundamental equations given by Newton. Okay, this is just a different mathematical approach to solve the problems. Okay, or in other words, we are trying to recast the Newton's second law in such a way so that we can deal with problems like this. Okay, along the way we learned something very important and new things about moving objects, their energies, and while studying their motion, how they interact with different forces. Right? So as I said, we begin with Newton's law. Okay. Let's say that we have an object at height h from the surface of Earth. All right. So the force acting on it is a force acting on it, and there is going to be an acceleration, a resultant acceleration. All right. So if I multiply the height on both sides. Okay, let's say that my acceleration and force are in just one direction and I deal with the scalar equation. Okay, forget about the risk vector. So let's say that force is acting in just this direction. There are no other forces, only in the y direction, and we are looking at the y component. Okay, and then we multiply h here. All right, and now let's say that this force is a constant force. It does not depend on the position h. So it's constant. It does not change the force as the object drops from this position to the surface of Earth. In such cases, the acceleration is also constant. You know that, right? And if we have a constant acceleration, we can always write the constant acceleration like this. The final velocity, square of the final velocity minus square of the initial velocity over 2h. So, right? Now, if you plug that back in here, you would get FH equals half mvf squared minus half mv I squared. Okay, very important relationship. Is it clear to everyone? Any difficulties about it? So this is very important. This is the beginning. So this quantity, this object here, force multiplied by the distance. Okay, that is what we call, or we define. This is what we call work. We say work done by force F. Okay, this is work, and this quantity here, I have two similar expressions, but let's say this is what we call the kinetic energy of an object, half of mass times the square of its velocity or speed. That is what gives me the kinetic energy of an object. Okay, what is this? Kinetic energy of an object. When I say half mvf, that means the final kinetic energy of the object, the kinetic energy of the object when it hits the surface of Earth. Okay, and minus half mvi gives me the initial kinetic energy of the object. So what this whole relationship, which we just got from the Newton's second law, is saying work done by a force, okay, in moving an object from some point to some point so that it covers a distance h or a displacement h, okay, is equal to the change in kinetic energy of that object. Does it make sense? I mean, the statement, I mean, you may still be grappling with the concept, how is work related to the kinetic energy, but the statement, is it clear? Work done by force F in moving an object distance h is equal to the difference in its kinetic energy at the final position minus the kinetic energy at the final position and the kinetic energy at the initial position when it started. Now, any questions, please?
सर एक चीज मैंने पूछनी थी कि इसमें जो फोर्स है और एक्सेलरेशन है वो हम यही सोच रहे हैं कि वो कांस्टेंट है, राइट?
हाँ जी, बिल्कुल बिल्कुल. अभी we will generalize it in a minute. For the time being, both acceleration and force have been assumed that they are constant. Okay, and as Ariva just asked about the force, this is not the most general definition. This is not a very general relationship because we can have other situations. For example, let's say that in this case, the one that we considered was more like this, that you have a block and you're pulling on it in this direction, and then the block moves a distance h or s if you like. Okay. Moves a distance s, and you're exerting a force in this direction, a constant force in this direction. All right. So the relationship between work and energy turns out to be simply Fs, like previously, half mv f squared minus half vi squared. All right. But what happens if this is not the situation, and the situation is this, that you cover a distance s from here to here, let's say, while you exert a force in this direction. What about this? Okay. Is the work still simply the product of the force and the distance? No. So we need to work out. So we need to resolve the force into two components. The force being exerted along this direction, let's say the angle is theta. So then you have the x component of the force is f cosine theta, and this is f sine theta. All right. Now if you work out so now the work is f cosine theta times s half mvf minus half mvi squared. Okay. So if you look, how about the work done by moving the object from here to here if I'm exerting the force in this direction?
जीरो हो
Zero.
जाएगा ना.
Zero, because the component along this direction is one, is sorry, is zero. How about if the force is being exerted in this direction? All the force, and this is the displacement. Then F times S हो जाएगा. Okay. So do you so between these two extremes, actually, between Fs and zero. So do you know a mathematical relationship between two vectors which gives you this? Hmm?
perpendicular होता है ना उनका प्रोडक्ट आई थिंक. आई
This
मीन
is
उनका प्रोडक्ट अगर वो दोनों परपेंडिकुलर हो तो जीरो होता है यूजुअली जब दो वेक्टर्स
कौन सा product?
जब दो वेक्टर्स परपेंडिकुलर होते हैं तो उनका डॉट प्रोडक्ट जीरो नहीं होता.
Yes, exactly. So the mathematical operation between two vectors which gives us this property is a dot product. Okay. F dot S, what is it equal to? Fs cosine theta. Now, depending on the angle between force and the displacement, if the angle is 90 degrees, the work done is zero. If the angle is zero, the work done is simply Fs. And if theta is in between, is greater than zero, less than 90, then the work done is simply Fs, and the value of multiplied by the value of the cosine of theta. See this? So this is not the most general definition of work then, okay? So it's a bit general now than before. So we should actually write F dot S between, and the answer would be scalar, of course, because on the right hand side I have all the scalars. Half mv f squared minus half mv I squared. Okay. So this is better, right? But this is still not the most general definition, and I'll come to the most general definition in a minute, in a moment. But before I do that, let me just digress a little bit very quickly and say a few words about the dot product. So you all know that dot product between two vectors is AB cosine theta, but it's important to appreciate that it's also can also be equal to AX BX plus AY BY. Okay, what is the difference? Anyone?
सर ऊपर वाले में मैग्नीट्यूड आ जाता है और नीचे वाले में उसकी पोजीशन वेक्टर आ जाएगा.
Yes. So if you know the magnitude of two vectors and the angle between them, then this is how you can calculate the dot product. If you know the magnitudes of two vectors, okay, and the angle between them, if you know what A is and if you know what B is, then you can use the first expression. But instead of knowing that, if you have two vectors like this and you don't know what the angle between them is, but you know their x coordinates, AX, BX, AY, BY. So if you know their components, okay, then you can just multiply the components in this order. You can calculate the dot product. And you can also take the derivative of a dot product. Let's say you're taking it with respect to time, okay, or it could be with respect to any parameter that these vectors depend on. And the derivative would be simply the derivative of first vector with respect to time dot product with the second vector plus first vector derivative of the second vector with respect to time. The important bit here is that the derivative does not change the nature of a vector. It keeps it a vector. It may change its functional shape. So of course the derivative of the vector, but it so no. So I should say this: derivative of a vector, a scalar derivative of a vector, is another vector. Okay, that is why you still have the dot product. Otherwise, there will be problem in the equation. So this is the equation now, where C is the derivative of A with respect to time dot B plus A dot D, where D now is the derivative of another vector, which is the derivative of the vector B. Okay, this we would be using later on.
सर
Yes.
आप प्लीज ये दोबारा कॉन्सेप्ट समझा सकते हैं, मुझे सही से समझ नहीं आ रहा वेक्टर वाला सारा.
Simply ये तो समझ आ गया ना, कंपोनेंट्स और मैग्नीट्यूड्स वाला तो.
जी बिल्कुल.
So yeah, it's a dot product of two vectors. When you take the derivative of a dot product of two vectors, it is very similar to what you do with scalars. You take the derivative of the first vector, this, and it remains a vector actually. After taking the derivative, if you take a scalar derivative, like with the time derivative of a vector, the answer is again a vector. Okay, so this object is a vector dot product with B plus, then you leave the first vector and then you act on the with the operator on the second vector, which remains a vector again, and then remains a dot product. So that's it.
तो सर इसमें सिर्फ ax और b x की वो डेरिवेशन हुई है, ay by की नहीं हुई भी जो ऊपर है. अच्छा
जी
बल्कि नहीं, I got it. Never mind.
all right. So
सर एक और क्वेश्चन है, अगर अगर फॉर इंस्टेंस उसमें तो आपने मैग्नीट्यूड्स को वो किया हुआ है, तो अगर आप पोजीशन में करना हो तो फिर वो भी इसी तरह ही करेंगे.
जी
अगर इसमें तो आपने डॉट प्रोडक्ट जो है आपने मैग्नीट्यूड्स का लिया हुआ है, अगर इसके अंदर पोजीशन का लेना
नहीं
हो तो
नहीं
वो भी
नहीं नहीं मैग्नीट्यूड्स का नहीं लिया हुआ, वेक्टर्स का लिया हुआ है.
अच्छा ठीक ठीक ठीक.
ठीक है, वेक्टर्स का लिया हुआ है. डॉट प्रोडक्ट तो आप बाद में लेंगे ना, डेरिवेटिव पहले लेंगे. डॉट प्रोडक्ट नहीं ना एवेल्युएट की. डॉट प्रोडक्ट में वो चॉइस है मैग्नीट्यूड या कंपोनेंट्स. हमने डेरिवेटिव लेना है वेक्टर का, उसके कंपोनेंट्स का डेरिवेटिव लेना है, लीनियर है.
जी ठीक ठीक, थैंक यू.
ठीक. So more on the definition of the work and the relationship between work and energy. So work is, and I'll explain. Okay, so work is usually, actually always, is work done by a net force. Okay, work done by a net force means either that you take all the forces and you sum them vectorially, and whatever the net force you get, then you multiply it with the displacement using this relationship F dot S, and that gives you a quantity which we can now call work. And we have used the Newton's second law to also show that it's equal to the difference in the kinetic energy of the object at two different points, right? So what we mean by net work is the result of a net force, or you can also write the work as sum of each force, work done by each force, okay, and then you would have the net work as well. So work done by the force 1, work done by the force 2 in moving an object, plus work done by a force 3. Okay, and you see that I'm writing the same displacement, because if the object has to remain intact, it must have the same displacement vector unless you're tearing it apart. The object, however many forces are acting on it, if the object remains intact, so it has to have the one same displacement vector. And then this would give you work done by force 1, work done by force 2, and just adding those work, and work is a scalar, okay, then you get the total work. Another important thing here is, as is with the dot product, the work can be negative. Okay, if a force is acting in an opposite direction to the displacement, okay, then the work done by such a force on this object would be, if the angle is 180, exactly 180, then the work done by this force on this object would be simply minus Fs. All right.
सर
So
इसकी कोई एग्जांपल दे सकते हैं?
हाँ जी, करते हैं, अभी एग्जाम्पल करेंगे लेटर इन द कोर्स।
सर ये जीरो नहीं होना चाहिए
क्यों?
क्योंकि वो बिल्कुल ऑपोजिट है
हाँ, नहीं नहीं नहीं, जीरो होता, देखे ना, ये डेफिनेशन है, लुक एट दिस डेफिनेशन, डॉट प्रोडक्ट, ठीक है, वर्क नेगेटिव हो सकता है, जीरो नहीं होता। वर्क कैन बी ओनली जीरो when the object is, the displacement is zero or the net force is zero, otherwise there is always work. Okay, doesn't matter which orientation the two are happening. Okay,
ठीक है सर
yes, a work can be zero, for example, since it's a dot product. If work and displacement are orthogonal, then work is zero. If the force is in this direction, S is in this direction, the work done by such force on this object would be zero. Okay, again, that's why F dot S always. Look at this quantity. Okay, this would give you the correct sign of the work as well, negative work or positive work. All right. And that's why it's always a good practice to work with the coordinate system. So let's say we have an object here, okay, and you're pulling on this object in this direction, and it is moving in this direction. All right. So, and the coordinate system is such, this is Ex, this is Ey, right? Now let's account all the forces that are acting on this object. The external force that you are applying, F, and then if you're making angle theta with the horizontal, there would be an X component of this force, x f cosine theta, the y component of this force x sine theta, of course the, and let me just write them in vector form. This force is f cosine theta ex plus f sine theta ey, all right? And then there is a, let's call it force P, let's call there is a force of gravity, which is minus mg ey pulling downwards. And then there is a normal force, which is equal to mg ey, all right? Any other force here? Just these three forces where one of the forces has two components, okay? So now we write the displacement vector, okay, in the same coordinates. And the displacement vector is simply s, some displacement s is in the positive ex direction, okay? So now we take these forces, all the forces, and we calculate the work done by net work done on this object, okay? The net work done on this object, fs, okay? So if I write all the forces together, then in the x direction I have f cosine theta ex, okay, just one force, one component. Then in the y direction I have the normal force, this one positive. Then I have the weight, okay, minus mg. It's actually better if I just take its magnitude and not say that it's a normal force, because this is more general. N minus mg, negative for the force in the negative direction, the weight, the normal force is in the upward direction, and then there's a y component of the pull that you're exerting, okay? F sine theta ey. All these forces are in the y direction, okay? Parallel or anti-parallel. Or this is also positive. So this is all F, and then now dot product with this vector by this vector S Ex. Okay. So if you take the dot product with each term, you would get F cosine theta and Ex dot Ex, right? So this is work done by the X component of the pull, this piece of work. Okay. Then you have the next piece work where you have N times S again with Ex dot Ey. All right. So work done by this piece of force. Okay. This piece of work is due to this force, normal force. Then you have mg s ex ey. Okay. And then there is a fourth term at the end, which is plus f sine theta ex ey. Right. So this is again the same concept here. The work done by each force you can calculate, and then in the end you can sum all the forces. Luckily for us, this is very simple. This is Ex Ey. This dot product is 0. Ex Ey. This dot product is 0, and this dot product is also 0. So we get the same, and Ex is 1. So we get the force work done by such an expression. In such a situation, the net work done is simply f cosine theta.
Sir,
Yes.
We will also multiply S with F cos theta and F sin theta, right?
Oh, yes, yes, yes. Did I miss that somewhere? Yes, there is an S here, sorry. An S here, and S here, and here I have done that already. Yes, yes. So this would be Fs cosine theta. Yes, 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 absolutely. I mean, because we're doing that, this is the magnitude and that's dot product. Okay. Okay, so we have a fairly general description of the work and the force. But let's say, because in the case that I considered in introducing the work energy, the very first definition, I assumed that force was they are zeros, and of the x components, the dot product. This is this is why they get cancelled, because this is too crowded here. This is why they get cancelled, and if you have a vector along ex, this unit vector, and then if you have another vector ey, I was just trying to make the concept of adding the work, otherwise I shouldn't have written all the rest of the terms. But the dot product in these two vectors, you can always write it like this, ab, and then I was writing an inner product between ex dot ey, the dot product between two unit vectors. They always make a 90 degrees with each other, okay? Or if you can see that these vectors are making 90 degrees with each other, so their dot product would be 0. The very first example that I used to introduce the relationship between work, or the introduce the concept of work, and somebody asked there that was the force was not dependent on position. I assumed a constant force, okay? But then that's that's very inconsistent with the motivation that we started this whole thing with. The motivation was to deal with the forces which depend on the position, because if the force does not depend on the position, then Newton's laws work really well. We don't really need a new formalism, the one that we are trying to develop. But then that was to introduce, and that's why the whatever we have done so far is not the most general definition of work, or the relationship between work and the energy. So now let's generalize it. Okay. Let's say that you have a force which depends on x, okay, which changes with the position. So let's say the force from going from x1 to x2, the force linearly changes. But it depends on position. Okay. So then, and there are examples of such forces, a lot of examples of such forces which depend on position, gravity being one. Okay. So how do we then work out? So the simple dot product, if I write like we did before, F dot S would be incorrect. Why would it be incorrect, someone? Abdur Rahman. Or anyone else? No one? Because in this product, I just have one component, one value of force, one number that corresponds to the force vector. Okay, but here I see that the force is different from going from here to here. So which force should I multiply the displacement with to get the work? The force now depends on the position. The only way out is that if I split the displacement into small intervals, and you are all too familiar with this trick by now, So if I split it into small intervals dx, okay, or ds, okay, doesn't really matter. And then here I can assume that the force has a certain value, and since this interval is very small, the force is going to have just the same value, or any change in the force is not going to be significant. So I can calculate the tiny amount of work that the force would do in covering this tiny distance. Okay, so I can write, and in the first interval, let's say I have the magnitude, the force, the value of the force is F1. It's going to be different in every interval. And then dot product dx. Okay, this would be the work done in this first tiny interval. You can call it interval 1. Then I can calculate the work done in the next tiny interval. But of course, this time the value of the force would be different. This time, in the first band or this interval, the value of the force is this. The second one, the value of the force is different, but it is going to be the same for this tiny interval, right? So I take a dot product of this force 2 dot dx2, the second interval, right? And I can construct n intervals, okay, or infinite intervals, so that they become really, really small. Okay. And if I sum all those pieces of work from 1 to n, then that would be the total work done by a variable force. And now you know that if we take n to infinity, this is Riemann sum, and Riemann sum is nothing but the integral from x1 to x2 f of x dx. Sorry, this is not, it's a vector equation. So it is f of x dot dx. Okay, and that would be the most general definition of work. Is for a force that depends on position. Any questions about this from position x1 to x2? Yes.
Sir, can't we just find the work done to get to x2 and subtract the work done to get to x1?
From where?
If we find the work done to get from origin to x1, or from the start to x1, and
Yes, but that,
subtract that.
yes, but then you still will have to do the two integrals instead of one. So you're saying do this 0 to x2 right? Or are you suggesting the geometric method that we calculate the area under the curve somehow geometrically?
No, I was thinking we already the equation जो हमने पहले define किया था f.
Then that would be incorrect. So yes, that may work in this case because the function is very well behaved. But how about this one? If the force is like this, can you do that now? Can you find out work just the simple function multiplying f? Because if you multiply f with x, okay, it would not give you the area under this curve, okay? So you would multiply this f with x2, it would give you this area, okay? And then if you multiply f with x1 again, it will give you this area. Now the difference of these two areas is not this area.
Yeah.
Okay, so this is the more general. Yes,
सर जो आपने ऊपर समेशन वाला इक्वेशन लिखे इंटीग्रल वहां भी नहीं लेना हमने
जी,
सर जो आपने समेशन वाला इक्वेशन लिखा है वर्क के लिए हम वहां भी इंटेग्रल नहीं लेंगे
नहीं, वो तो इंटेग हमने ये किया था शुरू के लेसन्स में कि रीमान सम इज इक्वल टू इज एन इंटीग्रेशन, नो?
ठीक
सो
है
ये तो हमने सिंपल वो जो जो पहली डेफिनेशन की है कि यू द डॉट प्रोडक्ट ऑफ द डिस्प्लेसमेंट एंड द फोर्स गिव्स यू द वर्क, ओके, but force depends on the position, so we could not simply take the whole dot product of all the x. We simply, because force is different at different positions of x, so we what we did is we did calculate the work in the small pieces, and then we added them up, and then we argued that this is nothing but the integral. But I don't understand what do you mean by using the integral in the equation here. I mean, if you know this concept, once you're familiar with it, you don't really always have to write a sum. So you always know that if the force is position dependent, you have to integrate to get the work.
okay thank you sir
Okay. So now a little bit more. So how about this? Now let me just make this extend this argument, because when we did this original derivation or the original introduction, we simply multiplied h with the Newton's law on both sides, and then it was very obvious. It's very straightforwardly followed that we could write the work done equal to change in the kinetic energy. But this is not very straightforward. So we are not sure that this work is equal to whether this work is equal to change in kinetic energy of the object or not. So we will try to show it more explicitly. Okay. So let's say that we have a tiny bit of work that we do for while we move an object from some point A to B, okay, using some force, and and this would be equals to, I'm sorry, let me just rewrite and then work backwards. That would be better. So let me just write this, that work is between 2 points A and B is nothing but force, a dot product of the displacement vector. Okay, so this is work in the integral form that we just worked out for a variable force, and we say that this is the most general definition of work. And now instead of taking all the work, let's take the tiny bit of the work. Okay, a tiny bit of the work. Okay, and after doing that, can I write mdv over dt times ds, or no? Can I do that? Oh, sorry, not
Yes,
ds, not ds, dt actually. Or let me just make sure that ds and yes, m, and then we have the acceleration, right? So we can write that dv over dt. That is fine, right? This is the first bit. Then dot product ds, right? So we can write like that. Can we also write it like this? M dv over dt, and then dot product v dt. Can we also write that? Can we write ds as v dt? No? Oh, yes.
Yes.
All right. So now let
सर
me
ये डी को VDD कैसे लिखे?
जी
ये DS को VDT कैसे लिखा है?
ये ऐसे लिखा है, इससे आप इत्तेफाक करते हैं s is equal to vt.
Yes sir.
So for a small, let's say that an object moves with velocity v for a very small amount of time, and I'm saying it covers a small distance ds. No?
ठीक है सर, समझ आ गया.
Right? So now I have this expression, and to simplify it, I'm going to use a reverse derivation. So let's start with this object here. And remember the thing that we talked about, the dot product. We're taking the dot product of v dot v. Okay? Velocity dot product with velocity. Okay? Now if we use the vector product, it turns out to be dv over dt dot product v plus v dot dv over dt. Right? And do you also know that dot product commutes? That a dot b is equal to b dot a. Do you know that? So that is simply dv over dt dot v. And from here, I can write dv over dt dot v is half dv dot v dot. Okay. Let me know if you're struggling. How did I get this relationship? The one in the box.
Sir, can you repeat the part about when you
Repeat.
v
Ji.
times v? The differential of v times v, what does it represent?
It doesn't represent anything for now. Okay, it's a reverse derivation. I'm saying I take two vectors, two identical vectors, a vector, and take its dot product with itself. Okay, then I take its derivative. Okay, now we know the rules for dot product. We also know the rules for derivation and the derivation of the dot product. So what I write is the derivative of the first vector in the product dot the second vector plus the first vector dot the derivative of the second vector. Okay, and then I am saying after that the dot product commutes. If you take the dot product of two vectors, a dot b is equal to b dot a, that helps me write these two terms as just one terms two times. So this lets me add these two terms. Okay, it's 2 times dv over dt times v, and there is no physics here, just mathematics. So that means this expression can be written as half d v dot v.
सर वो dt कहाँ चला गया दूसरा
Oh sorry, dt भी है यहाँ पे. ठीक है. All right. Now you can substitute this back in here. Okay. Now it becomes d v dot d over dt into dt. Now this dt simply cancels with it.
सर ओवर 2 भी तो है.
Over 2 भी है. ठीक है. So what are we left with is m2 dv dv, right? The dt cancel. Or if you like, you can just simply write it. V dot v is what? V squared. The dot product of the same vector, right? So that is the tiny bit of work that a non-uniform force is doing, a force which depends on the position, right? And now we take this back into the integral here. Okay, this f ds, f dot ds, or you can just say that we are integrating on both sides. So this is dw. So you integrate all work done. So you add all small pieces of work. You do the integration here from a to b, and you do the integration here from a to b. The only tricky bit now is, and I'm sure that you would be confused, is whenever we do normal integration, let me use another board if there is space. Whenever you do the regular integration, see this. So you are integrating x1, and here you have dx. What is the integral?
Zero.
Hmm?
सर इंटीग्रल dx हो जाएगा बस, तो फिर x बन जाएगा.
इसका इंटीग्रल क्या होगा?
x बन जाएगा सर.
x. ये होगा ना इंटीग्रल. ठीक है. अच्छा, अब ये देखें, इसका इंटीग्रल क्या होगा?
Y.
y हो जाएगा.
y होगा. अच्छा, इसका इंटीग्रल क्या होगा?
और
r. शाबाश. अच्छा, अब ये बताएं कि इसका इंटीग्रल क्या होगा?
x स्क्वायर हो
X
जाएगा.
square.
x square. Very good. So I didn't have to spend all this time, eh? So you already know. If anyone is struggling with this, please now. Because whatever you have here, you're integrating with respect to that, okay? So that is exactly what we have here. So what would be this integral here? This is just constant, m by 2.
v square.
M by 2 v square at point B minus v squared at point A. All right. So we have just been able to show, and this is the total work here, that the total work, the net work done by a force which depends on position is again equals to the difference in the kinetic energy at the starting point and at the end point of the object. This is what I was trying to prove. Is it transparent to everyone?
सर
Yes.
ये एग्जाम में प्रूफ तो नहीं आएगा ना?
जी.
एग्जाम में ये प्रूफ तो नहीं आएगा ना?
I don't know, to be honest. आ भी सकता है. Now that you have asked, so I may be tempted to.
सर माइनर सा सवाल है, वो वन जो टू था वो 1/2 कैसे हुआ है जो आपने जब डिफरेंशिएट किया?
ये वाला 2.
सर वो कैमरा चेंज हुआ.
ओ अच्छा अच्छा. ये वाले 2 की बात कर रहे हैं.
हाँ जी सर. यस.
इसको इधर लाए हैं ना, इस तरफ. वो मैंने एक्सप्रेशन उधर लिख दी है. वो v डॉट v वाली इधर है ना, उसको इधर ले आए हैं.
ठीक ठीक ठीक. थैंक यू सर.
So the most general form of this relationship now, A to B F dot ds is equal to half mvb minus half mva squared. Okay, that is the work kinetic energy theorem. Okay, the relationship between work and kinetic energy, and this is the most general form. This is nothing new. It's just, you can think of it as, and it actually is, a recasting of the Newton's second law. As I said, the Newton's second law, as we write it, F is equal to ma. Is it in its differential form? If you write it, it's really a differential equation, and it is in its differential form. Dx squared over dt is equal to the force acting on this object. In fact, on the right side, and I don't want to jump ahead of myself, but once in a while it's fine. And in fact, the right side, yeah. So yeah. Just let's stay with force. Okay, let's stay with general force. Okay, so this is the form of the equation that we usually deal with. The Newton said it's a differential equation. It's in differential form. You can think of this as that this is the Newton's second law in an integral form. It's not anything new in terms of being fundamental, just a new relationship. Okay, so let's try applying something that we just knew, just learned. So let's say that we are throwing an object from the surface of Earth upwards. Okay, so we are throwing an object from the surface of Earth upwards. We want to figure out, so first, what are the forces? What forces are acting on it? Only one force, the force of gravity. And that is G M M over, so let's denote the position of the object at any time by coordinate y. So y squared Ey. And it's negative because the gravitational force is downwards, Ey. Right? And the displacement is dy Ey. Okay, this is the displacement. And the displacement is upward, so it would be positive. Now, what would be the work in this case? The work would be simply, let's say the work would be first the dot product of the force and the displacement. And what would be the limits in this case? We are throwing it from the surface of Earth, and we want it to get to some height h. Let's say if final point is h from the surface of Earth, the point of launch is the surface of Earth. The radius of Earth can be, because the force of gravity, the component in the force of gravity here is really the distance between the centers of the 2 points. So this y is from the origin. Okay, the origin in this case, or the y is 0 at the origin of the Earth. Okay, so we start with re, we go up to re plus h. This would be the limit, and this would be the total work done. So if I plug in all the coefficients, all the values of f and s, so what I get is re to re plus h, okay, g m small m over y squared dy. Okay. So I've just evaluated the dot product and they are anti-parallel. Okay, this is an example. The work done in this case is going to be work done by the gravitational force on the object in this case is going to be,
नेगेटिव
sorry,
सर नेगेटिव होगा ना कि फोर्स डाउनवर्ड्स है
negative,
और डिस्प्लेसमेंट ऊपर की तरफ है
because force is in this direction and the object is going. This is an example of negative work. Okay.
ये एक बार रिपीट कर दें ये नेगेटिव वर्क वाली.
It's very simple that whenever the force is anti-parallel or makes an angle which is larger than 90, okay,
ये समझ आ गई. मतलब मैं कह रहा हूँ मतलब ये ऑब्जेक्ट फोर्स और इसका मतलब जो है वो कैसे एंटी पैरेलल है.
देखिए हमने ऑब्जेक्ट ऊपर की तरफ फेंका ये, ठीक है, तो ये ऑब्जेक्ट जब ऊपर की तरफ जा रहा है तो उसका डिस्प्लेसमेंट की डायरेक्शन क्या है, ऊपर है ना.
जी सर.
तो मैंने कोऑर्डिनेट सिस्टम लिया हुआ है जिसका y ऊपर की तरफ है तो ये पॉजिटिव है, ठीक है. जब ये ऊपर की जा रहा है तो फोर्स ऑफ ग्रेविटी की डायरेक्शन क्या है,
नीचे.
नीचे, दे आर इन द ऑपोजिट डायरेक्शन.
जी ठीक ठीक.
सर आर क्या है इसके अंदर?
जी r is the radius of earth. ठीक है. So you can write the integral gmm 1 over re plus h minus 1 over re. So this would be the work done by the earth if an object goes from the surface of earth to a height h.
एक्सक्यूज मी सर
Yes,
आपका कैमरा है वो आउट ऑफ फोकस है तो आपने जो अब सही है
probably because I'm moving, so the camera loses focus for a while. So this makes sense. All right. So now we know that this work is also equal to the change in kinetic energy. Right? We can use this work calculated to some very useful purpose, for some very useful purpose. So I make two impositions on this physical situation. I say that I throw with this object with such a force that it reaches an infinite height, h becomes infinite, immeasurable. Okay. All right. So when I let that h to become infinite, then this term in the work becomes zero, the first term, because h is infinite, is in the denominator. Okay. So my work done simply becomes gmm over re minus sign, sorry, here. Okay. And then I also say that when it gets to infinity, it probably is not moving, it comes to rest. Okay, it becomes, so I throw it you throw an object up and it starts slowing down, right, because of the gravity. Okay, so I throw it with such a force that it gets to infinity, and the moment it reaches, by the time it reaches to infinity, it comes to rest, it slows down and then eventually stops. Its final velocity is zero. Okay, now if I impose those two conditions on this situation, okay, they give me something very interesting. The work done is equal to half mv at infinity minus half mv 0 at the surface of earth. Okay, now I'm saying this is zero, its final velocity is zero, and it has reached an infinite distance above the surface of Earth. So this term on this side is simply minus gm m over re. Okay. And I'm moving on to the next board, just taking this relationship, minus cancels on both sides, and there is a square here. So I get V naught RE in terms of these terms: R, the radius of Earth, the mass of Earth, and the universal gravitational constant. 2G. What is V naught now? Anyone?
Initial speed,
G?
velocity.
Escape
Orbital
velocity.
Escape velocity, because my physical conditions are such that I want the distance to get out of the to be infinitely away from Earth. Okay, and for ease, I say that when it goes to the when it's infinite distance away, it can come to rest. It is already at rest. So this is the velocity with which I must throw the object to achieve those two milestones. Okay, to be able to escape. G,
ये RE कौन सा डिस्टेंस है ये
that's the radius of
surface
Earth.
of Earth
That's the radius of Earth.
ठीक है
ठीक है. So this is called the escape velocity for any object. And you see, for any object, it does not really depend on the shape or the mass of the object, although in reality a little bit it does, but in general it only depends on how strong the force of gravity is of a given planet, let's say. So for every planet you can work out a escape velocity. Okay, so this is the velocity with which if you throw a ball upwards, it would never come back. Now, this was one use. Another use of the work energy theorem is that you can use the work energy theorem in a similar situation. In this case, if H was not going to infinity, okay, and if the distance above the Earth is not large, so you are throwing an object to a height H, and it's not a lot, it's not very large, so that you can take the force of gravity to be constant, F equals to minus mg, and just nearby the Earth, then the work done by this force would be simply what? Someone please?
Sir, mgh minus mgh.
Minus mgh. Okay, and then the work energy relationship in this case would be relatively simple. Minus mgh half mv final squared minus half mv initial squared. Okay, and sometimes we just use v and v naught, whichever you like. Okay, now the usefulness of this is that you can use this equation. Okay, although in this case, since we have taken the force to be constant, it's much simpler to just use the Newton's law. But for sake of understanding, it's given in your notes. Please go and do this using this theorem and try to find y as a position of time. It is as if you have solved this problem using Newton's law a lot of times, right? So whenever you want to find the position of a free falling object as a function of time, we have done this countless times, assuming that the force is constant, right? So still force is constant, but I want you to take this route. Start with this equation and arrive at y of t. You already know the answer, okay? But I encourage you to do it. So this would be it looks, but it's very important. It's important that we get the same answer if we use the two approaches. And again, just to emphasize that the work energy theorem is nothing but a restatement of the Newton's second law. Any questions so far? Because I am switching topics. I'm moving on to something slightly different than what we are discussing so far.
Sir, can you please explain why it's minus mgh again?
Again, because of the coordinate system. So the h is upwards and the force is downwards. That's why it's minus mgh. When an object is falling, then the work would be positive, because h would be negative and mg would be negative and the net work would be positive. So when an object is dropping, then its distance displacement is negative and the force is negative, and then the work would be positive.
Okay, thank you.
All right. So more. Now here again, the original motivation of introducing the work energy theorem and this new formalism was that you do not know the position vector, okay, as a function of time. But the work energy theorem also requires the information about the path, because you have to integrate the force along the path, right? If you move an object from here to here, you need to know the path, okay, because that's where you are integrating the force along. Okay, so there is path information that is very important, or that becomes very important. And then we end up with the problem, because if we knew the path information, then we would just solve the Newton's equations. So what saves us here is that most of the time the path information is straightforward to figure out, that we can figure out the path along which we have to do this integration. All right, for most cases. Then there is a whole group of forces where this integral does not depend on the path. Okay, and this is because of the nature of the forces. And such forces whose the work done by let me say, if work done by a force does not depend on the details of the path and is only depends on the final points, such force is called a conservative force. Okay, and for any force, for example, if you move an object from here to here, from A to B, okay, and then you take another path and move the object from A to B with another path, let's say 1, 2, and then you take a third path, okay, and in all three paths, along all three paths, if the work done by the force that is doing this work, okay, of moving this object from here to here, if it remains same, then the force is conservative. I'll explain this using examples, okay, just be patient for a second. This is a conservative force, and if the work done along path 3, path 1, path 2 is not equal, then such a force is called non-conservative force. Right? For our purposes, gravity is a conservative force. All right, and friction, for example, is a non-conservative force. Okay, electrostatic force, the force of attraction or the force of repulsion between electrostatic charges is a conservative force. Okay, all all forces which are called the central forces. Gravitational force is a central force. Electrostatic force is a central force. All central forces can be shown to be be conservative. Okay, force of friction is a non-conservative force. Um, I think we are running ahead of over time, so we'll finish this tomorrow. Okay. Thank you very much.